Hello students, today we are going to discuss the angular momentum, magnetic moment as well as electric quadrupole moment associated with deuterium nuclei, neutron nuclei, and in this discussion we are going to justify all the properties of the nuclear forces. So we are going to start with angular momentum. Experimentally it is known that the angular momentum and parity of deuterium nuclei is 1 plus. This is 1 plus. We are aware about this. Now we will consider this. We will explain this on the basis of some logical discussion. So basically inside the deuteron we have one proton and one neutron, and spin of proton is suppose sp, this is half, and spin of neutron is also half. So both particles, proton and neutron, inside the deuteron have half spin. This sp and sn, they are spin quantum numbers. But we cannot measure. These are not measurable. These are just quantum numbers. These are not measurable quantities. So what are measurable quantities? In case of spin, measurable quantities are square of the spin, and square of the spin is s plus 1, s plus 1. This is one of the measurable quantities, and this will be h cross square. Substitute here half plus 1 h cross square. So this will be 3 by 4 h cross square. This is a measurable quantity. So from here s will be square root 3 by 2 h cross. This is a measurable quantity. Another measurable quantity is the z component of the spin. Another measurable quantity is sz, z component of the spin, and this is plus h cross by 2 and minus h cross by 2. So these are two measurable quantities. So this term and this term, they are physically measurable quantities. Physically measurable quantities. Measurable quantities. This state. So basically there are two states of the spin, and this state is known as spin up state. This is represented by spin up state. This is known as spin up state. This is spin up state, and this is represented by this vector in the upward direction. And this state minus h cross by 2, this is known as spin down state. Spin down state and this is represented by this vector in the downward directions. So basically spin can have two states, one up state and down state, and if these two spin angular momentums are not coupling with each other, if two spin angular momentum vectors are not coupling with each other, then four states are possible. Following four states are possible. One state will be this one, both the proton and neutron. This is representing, first one is representing proton, second is neutron. This is the first state that is possible. Both have their spin in the up direction. They are in up state. Second will be this. Proton has up spin, neutron has down spin. So this is the second state. Third state that will be possible will be reverse of this. Proton has down state and neutron has up state. This is the third one. And the fourth one, both proton as well as neutron, they are in the down spin state. So these are the four states which are possible if the spin angular momentum of proton and neutrons are not coupled to each other. However, if the two spin angular momentums are coupled, then what will be the final S? Then final S will be, or you can say if SP and SN are coupled, then S will be equal to SP plus SN, and S, this spin quantum number, it will have two possible values. One will be 0 and one will be 1, because SP is equal to 1 here, SP is equal to half, SN is equal to half. So what will be the value of S? This will be from SP mod of SP minus SN to SP plus SN. SP plus SN, this will be the formula. This will be the formula, and from this there are only two states possible. One will be S equal to 0 and another will be S equal to 1. Now we will consider both these states one by one. So first I am considering this S is equal to 0 state. So first I am considering this S equal to 0. S equal to 0 state. So corresponding to S equal to 0 state, corresponding to this S equal to 0 state, Sz value will be 0. Sz value will be 0. Or you can say this Sz will be 0. And what is the value of Sz? This will be Spz plus Snz. And this is possible only when we have these two states. So this condition is satisfied in these two conditions. Either we have this state or we have this state. So these two states are possible here. So when S is equal to 0, then Sz will be 0. This will be satisfied only when we have these positions of the proton and neutron. So basically S equal to 0 state will be a combination. So S equal to 0 state will be a combination, of these two states. So this state will be corresponding to S equal to 0. Our state will be, normalized state will be this one. This state, which is a combination of these about two states, this will be the state corresponding to S equal to 0. Now come to the another example. Now come to the another case, S equal to 1. Now come to another case, second case, that is S equal to 1. Corresponding to S equal to 1, this Sz can have three values: -1, 0 and plus 1. These three states are possible. Basically, three Sz values are possible. Corresponding to Sz equal to minus 1, possible state will be this one. This will be the possible state. Corresponding, so both are in downward direction, so this Sz will be minus 1. Sz is equal to plus 1 will be corresponding to this state. Both these spins are in upward direction. This will be the second case. Now there will be third case, Sz is equal to 0. This will again a combination of these two states, and here it will be equal to, this state will be 1 by root 2, and here it will be combination of these two again. But you have to remember that this state is different from this first state. This is first state, second, third, fourth. These four states are possible. These three states are corresponding to S equal to 1, and this state is corresponding to S is equal to 0. So this state is different from this state, and they are orthogonal to each other. They are different states and they are orthogonal to each other. They are orthogonal to each other. So here we have corresponding to S equal to 0. This is one possible state. For S equal to 1, we have these three possible states. So if nuclear interaction or nuclear forces, are independent of spin, then deuteron nuclei should remain in this state for 25% time. So basically, corresponding to S equal to 0, we have one state. Corresponding to S equal to 1, there are 4 states. So the total number of states are 4. So corresponding, if nuclear forces or nuclear interaction is independent of spin, then the deuteron nuclei should remain in S equal to 0 state for 25% time and in S equal to 1 state for 75% time. 75% time. This should be the situation. This should be the situation. So if nuclear forces or nuclear interaction are independent of the spin, then deuteron nuclei for 25% time should be in S equal to 0 state, and for 75% time it should be in S equal to 1 state. We are aware that I value is for the deuteron nuclei is 1. And if we are choosing this S equal to 0, and we are also aware that L is also 1, L is 0 for the deuteron nuclei. For deuteron nuclei, L is equal to 0, and this I pi for deuteron nuclei is 1 plus. So if we choose S equal to 0, then this will give us only I equal to 0. But I is equal to 1 is experimental known, so this is not possible. This S equal to 0 is not possible. So if L equal to 0, we have only one possibility, that is S equal to 1. This will take us to I equal to 0. So here, out of these possibilities, nuclear forces chooses this S equal to 1. So only S equal to 1 is the possible state in which deuteron nuclei exist. And it means, what is the meaning of this? If deuteron nuclei chooses S equal to 1 and it is not choosing S equal to 0, if nuclear forces was independent of spin, then the probability for S equal to 0 state was 25%. For S equal to 1 state, it was 75%. It was 75%. But here, experimentally, it is known that that for all the time, for 100% time, deuteron nuclei will be here in s equal to 1 state. Deuteron nuclei will be in only s equal to 1 state. So this is the possibility. These nuclear forces are choosing this s equal to 1 over s equal to 0. Even by logic also, only s is equal to 1 possible. Even there is a case, here we are assuming that there is central potential. If we later on we will show you that if we are choosing even non-central potential, then value of s will be 1. Value of s will be 1. It means nuclear forces are choosing this s equal to 1. This is not possible. They are not choosing this s equal to 0. They are choosing this s equal to 1. So nuclear forces are preferring this s equal to 1 state compared to s equal to 0 state. It means they are favoring, nuclear forces are favoring the s equal to 1 state, and they are not favoring s equal to 0 state. So from this discussion, we can conclude that nuclear forces are spin dependent. They are spin dependent, and s equal to 1 state is possible. Only s equal to 1 state is possible. S equal to 0 is not possible, and these three states are possible. These three states are possible. Now come to the another aspect. Here we are observing that this I is equal to 1 experimentally. Now with the help of this, I will show you another aspect of the nuclear forces. Up to this point, we have assumed that nuclear potential is central potential, but I will show you here that the nuclear forces will also have, it can have or it may have a non-central part. How we can show? With the help of this angular momentum. Here this I is equal to 1, so I am writing here that I should be 1 for deuteron nuclei. How can we obtain this? So if we are taking s equal to 0, then here with this L can be 0. In this case, this I will be 0. So in this way we cannot obtain this I equal to 1. So this is not possible to obtain here. It is not possible to obtain here. Another is s is equal to 0 and you are choosing L equal to 1. So here in this case I can be 1. But what will be the parity? In this case, parity pi will be equal to minus 1 to the power L, and this will be minus 1 to the power 1, and it will be negative parity. So parity will be negative. If we are choosing this combination of s equal to 0 and L equal to 1, then parity will be negative. So this is also not possible because parity is positive. For deuteron ground state, parity is 1 plus, this parity is plus. So this case is not possible. If you take other values of L like 2, 3, 4, then I will never will be 1. So these are also not possible. So s is equal to 0 is not possible. For this state, we cannot, with the help of s equal to 0, we cannot explain this 1 plus state. Now take s equal to 1, and if we are taking L equal to 0, then this will be equal to, I will be equal to 1. So I will be 1. S equal to 1, L equal to 0, what will be the parity? Pi will be equal to minus 1 to the power L is 0, so this will be 0, so positive parity. So we can have this combination. This combination can provide us, so this combination can provide us this 1 plus state. This is okay. Now take L equal to 1. So S equal to 1, L equal to 1. So what values of I are possible? 1 minus 1, this will be 0. 1 plus 1 will be 2. So it will be 0, 1, 2. These three I values are possible. So 1 is here. So 1 is here. Now find out pi. What will be the value of pi? This will be minus 1 to the power L. L is 1. So this will be negative. Negative. Parity is negative, but here parity is positive. So this is also not possible. This is not possible. Now I take L equal to 2. So what value of I are possible? This is 2 minus 1. This will be 1. It can be 2. It can be 3. And parity in this case will be minus 1 to the power 2. So this will be positive. So this 1 plus state, 2 plus state. So here this 1 plus state can be obtained with the help of this combination also. So we can obtain this with the help of two combinations, S equal to 1, L equal to 0, S equal to 1, L equal to 2. So these two possibilities are there. If you take L equal to 3, then you are going to get I equal to 2, 3, 4. So we are not getting I equal to 1. So we are leaving these cases, further cases. So this, if we are choosing S equal to 1, then there are two possibilities, L equal to 0 as well as L equal to 2. So from this we can say that the ground state is made up of two L values. So there are two L values which are possible for the ground state of the deuteron nuclei. Then how is this possible? If you are choosing central potential, then in case of central potential, value of L is always fixed. But here, if we are choosing these two states, then we have to say that the ground state is made up of these two states, or the ground state is a combination of these two L values state. However, this is possible. This can be made possible. How it can be made possible? If you assume that your PET potential is non-central. In case of non-central potential, it is possible that a wave function is made up of more than one L values. It can have more than one L values, or in case of non-central potential, a wave function can be made up of more than one L values. However, parity for all these L values should be same. This is the condition. So these two states, it is possible that the ground state, of the deuterium nuclei, psi d, it is made up of two states. It is a combination of two states. One state corresponding to S equal to 1, L equal to 0. What will be the state? This will be S. Its multiplicity will be 2S plus 1. So this will be 3. J value will be 1. While for this will be 3D1. So this can be a combination of 3S1 plus B psi 3D1. So it is possible that the ground state of the deuteron nuclei is a combination of these two states. But this is possible only when we have known central potential. So from here, from this discussion, we can have one hint that the potential can be known. Whatever potential we are choosing as central potential, that can also have a non-central potential. And if we choose non-central potential, or our potential has a part which is non-central, then the ground state of the deuteron nuclei will be a combination of these two states. It will be a combination of. So from this discussion, we find out that the ground state is possible with these following two options. So from this discussion we can say ground state of the deuteron nuclei is a combination of these two states. One is 3s1, another is 3d1. Now question arises, how this is possible? This is possible if our potential, whatever potential we have assumed, if that has a known central part. If that has a known central potential part, then this is possible. So we have concluded from here two things. One, that the ground state of the nuclei is made up of, is a combination, you can say it is a combination of two states, 3s1 and 3d1, and its VR potential, this potential has a known central potential part. It has a known central potential part. Now, so these two things we are aware now. Next important thing is, if this nuclear forces or nuclear interaction is dependent on spin, then the potential VR, it should also have a spin dependent part. It should also have a spin dependent part. Now we have to find out that spin dependent part. We will have to find out that spin dependent part. So this spin dependent part should be constructed in such a way that whenever it is applied, whenever we have s equal to 0 state, then the potential value, the depth of the potential value should be decreased. So this spin dependent part should be in such a way that this spin dependent part will decrease the depth of the potential well when spin s is 0, and it will increase the depth of the potential well when s is equal to 1. So we have to construct, now we want to construct this spin dependent part of the potential. So for this, first we will calculate, if we want to find out this, first we have to calculate the value of sp dot sn, because if there is a spin dependency, then that spin dependency will depend upon sp dot sn. sp dot sn. So first we have to find out its value, sp dot sn. We can find out this value very easily, because for deuteron spin vector, spin angular momentum vector, this will be sp plus sn. So s vector dot s vector will be equal to sp vector plus sn vector dot sp vector dot sn vector. sp dot sn vector, this will be s square, this will be sp square plus sn square plus 2 times sp dot sn. So from here, this sp dot sn, what will be the value of sp dot sn? sp dot sn, its value will be equal to s square minus sp square minus sn square divided by 2. Now what is s square? It will be s plus 1 h cross square. What is the value of s for deuteron? This will be s is equal to 1. We are considering s is equal to 1 state. So for s equal to 1 state, or here you can write for s equal to 1 state, this will be 1 plus 1, this will be 2h cross square. For s equal to 0 state, this will be s square will be 0. This sp square, what will the value of sp square? This will be 3 by 4 h cross square. This sn square, this will be equal to 3 by 4 h cross square. So for s equal to 0, for s equal to 0, this sp dot sn, what will be the value of this sp dot sn? So this will be 0 minus 3 by 4 h cross square minus 3 by 4 h cross square divided by 2. So this will be equal to 3 by 4 h cross square. Its value will be 3 by 4 h cross square with negative sign. Now calculate for s equal to 1. What will be the value of sp dot sn? sp dot sn, then its value will be equal to 2 times h cross square minus 3 by 4 h cross square minus 3 by 4 h cross square divided by 2. So what will be its value? Calculate this. This will be h cross square by 4. h cross square by 4. Now if we want to construct an operator, for which the depth of the potential well, corresponding to which depth of potential well will increase for s equal to 1, and depth of potential well will decrease for s equal to 0. If we are in search of such type of operator, then the best choice we have, that is spin exchange operator. So for this we will choose spin exchange operator. For this purpose we will choose spin exchange operator. Spin exchange operator. Basically, with the help of this spin exchange operator, we can write that the nuclear interaction is choosing one spin and it is rejecting another spin. What is the expression of spin exchange operator? This is P sigma. This will be equal to 1 by 2 1 plus 4 upon h cross square, and this will be sp dot sn. This is the operator. If you are choosing s equal to 0, then what will be the value of P sigma? If you are choosing this value, so sp dot sn, it will be equal to minus 3 by 4. This will be here, this will be minus 3 by 4 h cross square. So this will be 1 by 2, or you can directly calculate this 1 plus 4 upon h cross square. This will be minus 1 3 by 4 h cross square. So this 4 will cancel out, this h cross square will cancel out, and here we will have minus 2 divided by 2, so we will have minus 1. So this P sigma will have its value as minus 1. For s equal to 1, you will find out what is this. For s equal to 1, this is h cross square by 4. So if you substitute here h cross square by 4, so this will become 1 plus 1 divided by 2, so it will be 1. So value of P sigma will be plus 1. So spin exchange operator has value plus 1 and minus 1 for s is equal to 0 and s equal to 1. Now with the help of this spin exchange operator, we can write the spin dependent part of the potential. So this will be VR. This is the central part, central potential part, VCR, plus V sigma R. This is the radial dependent part, multiplied by P sigma. So when spin s is equal to 0 is considered, then its value will be minus 1 here. So depth of the potential well will be decreased. While when this P sigma has plus value, then depth of the potential well will be increased. So in this way, we have constructed the spin dependent part of the central potential. So this central potential also has a spin dependent part, and due to this spin dependent part, nuclear forces favors one type of spin state, and they reject or they don't favor the other spin dependent state, other state of the spin. Second important property of the deuteron nuclei is its magnetic moment. Experimentally measured value of magnetic moment, its Z component mu Z is equal to 0.857 mu n. Mu n is the nuclear Bohr magnetron. Now, how can we justify this? Basically, inside the nuclei we have protons, we have neutrons. These protons are revolving in different orbits, so they are creating some current loop. Due to this current loop, we will have orbital angular momentum, and corresponding to this orbital angular momentum, there will be some magnetic moment that will be generated. However, when neutrons are revolving in the orbit, because charge on the neutron is 0, they are not creating any current loop. So, due to the orbital motion of the neutron, there will be no orbital angular momentum, there will be no orbital magnetic moment that will be generated. So, only the orbital motion of the proton is responsible for the magnetic moment generation. Apart from this proton as well as neutron, they are undergoing spin motion, and due to this spin motion, they also contribute to the magnetic moment formation or magnetic moment generation. So total magnetic moment or net magnetic moment of deuteron can be written like this. One can write the net magnetic moment of deuteron nuclei, that will be mu z. This will be GL mu n upon h cross, and here it will be Lz. This will be Lz. This is the first term, which is due to the orbital motion of the protons. This term is due to orbital motion of the proton, and here value of this GL is 1. Value of GL is equal to 1. Second term is due to the spin of the proton, so this will be GSP. The G values, they are known as gyromagnetic ratio, and this is gyromagnetic ratio for the spin of proton into mu n upon h cross into this will be SPZ, and value of this GSP is equal to 5.5691. This is the gyromagnetic ratio for the spin of the proton, and third term is due to the spin of the neutron, so this will be GSN mu n upon h cross SNZ. Here this gyromagnetic ratio due to the spin of the neutron, this is equal to minus 3.826084. These are the values. Now for the deuteron nuclei, we are aware that I is equal to 1. We are aware that I is equal to 1, and when we are going to measure, we are aware about this I is equal to 1, and corresponding to this I is equal to 1, Mi will have 3 values, plus 1, 0 and minus 1. Now from the measurement theory which we have studied in quantum mechanics, we are aware then that when we are going to measure experimentally the magnetic moment, basically if we want to measure the magnetic moment experimentally, then what we are going to find out? We are going to find out the maximum value of mu z. If you will try to find out, if you will try to measure the magnetic moment, and what will you get after the experiment? You will get the maximum value of mu z, and that maximum value of mu z will be corresponding to this mi equal to +1. So when we will measure experimentally the value of mu z, we will find out the mu z value, which is the maximum value of mu z, and that value will be corresponding to mi. This will be mi or is equal to +1. This will be mi is equal to +1. Now you are aware that I is equal to L plus S. So if this will be Iz, if I take Iz and here we take Lz plus Sz, so maximum value of this is +1, and this will be, what is the value of Lz? If we are considering the central potential, then value of L will be 0. If we are considering central potential, then this value of L will be 0, and automatically this value should be +1. So to satisfy this equation, value of Sz will be +1, and this Sz will be +1 when the spin of both proton and neutron, they are parallel to each other. So basically, when we are going to measure the value of magnetic moment, we are finding the maximum value of mu z corresponding to this state. We are going to find out the value corresponding to this state. Now operate this state over this mu z. So when we will operate this over this, then what we are going to find out? This is the eigenfunction, and when we will operate this mu z over this, then what we are going to find out? We are going to find out the average value or the expectation value. Actually, if psi is the wave function, of the Hamiltonian for this neutron nuclei, then it's not necessary that psi will also be a function of wave function of the mu z. So what I am saying here, that if psi is the wave function of a Hamiltonian of the neutron nuclei, then it's not necessary that this psi will also be a wave function of mu z. So if we will operate mu z operator over this psi, what we are going to find out? We are going to find out many values. But experimentally, what we will observe, what value we are going to find out? We are going to find out average value or the expectation value. So now we will find out the expectation value. How will you find out the expectation value for this? Basically, we will operate over this mu z here like this. We are going to find out this value. Experimentally, we are going to find out this value, average value or expectation value. We are going to find out this. Here, if we are assuming central potential, then L will be 0. There will be one state, ground state. In this case, ground state will be made up of only one state, that will be corresponding to L equal to 0. So ground state will be made up of only this state 3s1. In that case, this Lz will be 0. So in that case, this term will be 0. So what will be its value? Its value will be like this. Substitute this value here. So this will be GSP mu n upon H cross SPZ. Here this will be plus second term. This will be GSN mu n upon H cross SNZ SNZ. This will be. We are going to find out this value. Now we will solve this and we will find out what we are going to get. This will be equal, this is a constant, this is a constant. So here we will write this as GSP mu n upon h cross, and here SPZ this is a spin operator. When a spin operator for proton will operate over this, we will get h cross by 2 plus h cross by 2. So plus GSN mu n upon h cross this will be SNZ like this. So if we have SPZ, this is a spin operator over this wave function, then what eigenvalue we are going to find out? It will be h cross by 2 plus h cross by 2. Here is this is representing proton, this is representing neutron. Proton is in upward direction, so this will be plus h cross by 2, and here this will be the eigenfunction. Now second will be SNZ. Now this is the spin operator for the neutron, so it will operate on this neutron. This is neutron. This is again in the upward direction. It is in the up state, so this will again be this one. Now what you are going to get here, this will be GSP mu n upon h cross, and here we are going to get h cross by 2. This will be h cross by 2, and here this is bracket vector. Here its value will be 1. So these eigenfunction, if they are normalized, then the value of this will be equal to 1. Similarly here this will be GSN mu n upon h cross. This will be h cross by 2, and again this Bryant-Cat vectors. Its value will be 1. Value of this will be 1. Value of this will be 1. If eigenfunctions are normalized, this h cross will be cancelled out. This h cross will be cancelled out, and this will be GSN GSP plus GSN, and this will be mu n by 2. This will be mu n by 2. Now substitute these values of mu Sn. Now substitute the value of GSP as well as GSN. Values are given here, so we will substitute this. This will be equal to 5.585691 minus this GSN 3.826 into mu n by 2. If we solve this, we will find out that value comes out to be 0.8798 mu n. We are getting this value theoretically. So the expectation value or the average value when this mu z operates over this state, then we find out that the theoretical value comes out to be 0.8798 mu n, but experimental value is this. But this is the experimental value. This is the experimental value. So there is a discrepancy of minus 0.00. This is how much discrepancy is there? 0.0224 mu n. This discrepancy is there. So how will we justify this discrepancy? This discrepancy can be justified in this assumption. Here we have again assumed that that the potential, nuclear potential, is central in nature and the ground state is made up of 3s1. And because ground state is made up of 3s1, L is equal to 0, this first term is not contributing anything to this magnetic moment. But if we assume that, if we come to the earlier conclusion we have made in angular momentum article, that the ground state of the deuteron is made up of two states. One is 3s1 and another is 3d1. So ground state is a admixture of these two states. This is B, is a admixture of these two states. So here, if we assume that the ground state of the deuterium nuclei is a admixture of these admixture of these two states, then this state 3d1, this will contribute to L. Due to this 3d1 state, there will be some orbital angular momentum, and due to that orbital angular momentum, there will be some magnetic moment. So this term will start contributing. And this is possible only when we consider that the potential consists of a small but a significant non-central part. So if we consider a non-central potential, if the deuteron nuclei potential is non-central in nature, it consists of a non-central part, then we can easily assume, or we can easily conclude, that the nuclei ground state, here deuterium nuclei ground state, is an admixture of these two states. Here two L values are here, and this is possible only when we assume the non-central potential. So again, this discrepancy in these two values indicates that the potential is non-central in nature and the ground state of the deuteron nuclei is an admixture of two states, 3s1 and 3d1. So this discrepancy is hinting towards this. Again, in angular momentum article we have concluded to this point, and again in magnetic moment calculation we are coming to the same conclusion. Now next is next is electric quadrupole moment of the deuteron nuclei. Electric quadrupole moment of the deuteron nuclei. Next article is electric quadrupole moment of deuteron nuclei. Experimental measured value of the electric quadrupole moment of this deuteron nuclei is 2.88 millibar. This is Q value is plus 2.88 millibar. So here this is a small number. Quadrupole moment is small, but still this nuclei has this quadrupole moment. If we consider that the nuclear potential, again we consider that the potential is central in nature, if we again assume that the nuclear potential is central in nature, then again we will come to the conclusion that ground state is 3s1. We will come to the same conclusion. And here this represents L equal to 0 state. This is L equal to 0 state. So corresponding to this we will have a spherical symmetrical charge distribution. It means there is spherically symmetric charge distribution. Or wave function is, or wave function, we can conclude that wave function is independent of theta and phi. This conclusion we can make if we are assuming central potential. If we are assuming central potential, then we will come to this conclusion. So there will be a spherical charge distribution as well as wave function will be independent of theta and phi. So automatically quadrupole moment of deuteron nuclei should be 0. But this is not the case, but this is not correct. Experimentally we measure this value. Experimentally we measure that deuteron has a small quadrupole moment. Basically this deuteron nuclei consists of a very small but positive 2.88 millibar quadrupole moment. It means, what is the meaning of this? What is the meaning of this relatively small quadrupole moment which is not 0? It indicates that wave function of the deuteron ground state is not simple L equal to 0. So what we can conclude from this now, that the wave function is just not simple the state L equal to 0. Rather, it is a admixture. It is a admixture of L equal to 0 and L equal to 2 state. If we consider that the ground state of the deuteron is the admixture of these two states, and later on we can do, in numerical part, one can calculate that the probability of this state is 96% and probability of this is 4%. So if the wave function of the ground state is admixture of these two states, then automatically this L equal to 2 state will give rise to non-central component. This 3D1 part is due to non-central component, and this non-central component will be, or this non-central tensor component, which will be due to this part of the wave function, will be responsible for this quadrupole moment that is possessed by the deuteron nuclei. The interaction potential has a non-central tensor component, and this non-central tensor component is responsible for this quadrupole moment of the deuteron nuclei. So ground state, now we can confirm that by every calculation we are again and again finding that the potential is non-central in nature, it has non-central part, and the ground state is the admixture of these two states, 3S1 and 3D1, and this 3D1 part or non-central part, the tensor part, is responsible for the quadrupole moment that is possessed by the deuteron nuclei. So in this way we have discussed each and every part, each and every aspect of the deuteron nuclei.